Hello everyone, my name is Denis Vorotyntsev, and today I'd like to share with you my experience from participating in AutoGraph 2020 competition, which combines automated machine learning and graph data. So let's start by introducing myself. So currently I'm working as senior data scientist in Oura. We are making a wearable device which could help our users to optimize their sleep patterns. Probably one of the most famous of our projects is recent early COVID detection, in which we are using raw data and machine learning to detect first symptoms of COVID and advise our users to go to doctor and get tested. We have several partners there, including NBA, Women NBA, and NASCAR, and many others. Prior to my work in Oura, I was working in VTT, Research Center of Finland. I was a research scientist. We were making a machine learning model to identify problems during steel production and try to minimize those problems. So, as you understand, I'm not working with graph data day to day, but I'm really interested in participating in automated machine learning competition. So that's why I decided to participate in that competition in AutoGraph 2020. What we will cover today. So I'll start by describing what we need to do in that competition. Then I will briefly describe my solution. I will share some machine learning tricks which might help you in upcoming automated machine learning competitions. And then I will describe most interesting solutions from top 10 participants. So let's start. In this competition, participants were given several datasets, and for each dataset we need to create a model in an automated way. So we're basically writing a code which can produce models which are going to be used for making predictions for those datasets. And it was 10th, or maybe not 10th, competition on AutoML organized by FOPA and Charlie, and these guys are pretty experienced in organizing those competitions. So in this particular one, in AutoGraph 2020, we were giving several graphs, and we need to classify nodes of those graphs. So some of the nodes, so basically nodes were split into train and test part, and we need to make a prediction for test part. The metric of each dataset was accuracy, and the final metric is ranks of all datasets of all tasks. So basically, every participant submits his solution to the platform. His model is trained on the platform. Then model makes predictions for unseen data, and the metric accuracy is calculated for each of 5 datasets, both in the private part and in the public part. Then scores of all participants are ranked, and then the average rank is taken, and the person who showed like the best score among all datasets win. So our input data in such case is several files. So the first one is config, which is just a dictionary with very useful information, such as number of classes, names of features and their types. In this competition, participants only had numerical type of features, and also in config time budget is specified. So time budget is number of seconds, which is available both for model training and for predicting. Also, we're giving files such as HTSV with information on nodes and weight of edges between those nodes. We're given features TSV It is a file which contains information on features for each node in the dataset. In some cases, there was no features for nodes, and we need to somehow overcome this problem. And also we're giving train labels and list of node IDs in train and test part of the data. So we're giving this data, and our task is to write a class which has several functions within, functions such as train, which trains a model for a given input data, a function predict, which uses trained model to make a prediction, and basically train predict, which is called during the inference. It doesn't seem like a hard solution, but unfortunately it actually is hard, because if you are going to participate in automated machine learning competitions, you will learn that when you're trying to improve the score on a single data set, most probably scores on other data set will degrade, and it's not a desirable outcome. So in automated machine learning competition, we need to create a solution which, in the best case scenario, of course, perfectly fit all data sets, but in the realistic scenario, fits all data sets, but no data set perfectly. My approach in this competition was to follow this simple script. So basically, we start with our data, we create some additional features, then we split our data in train and validation part. It is not common in machine learning, so in general machine learning, before creating features, you first will split your data to avoid leakages. But in this competition, to make my pipeline easier, I decided to create features at first. It's not very correct, but I did that. I think I don't have too many leakages in my feature engineering approach by doing so. Anyways, we create additional features to split our data. Then we train several models. We make predictions for both validation and test part, and then we just stack or blend our predictions using model of second level model. Let's cover every part of the solution in more details. So we start from data processing, and data processing is basically is all about creating new features. So if we don't have any features at all, I created one hot and cold representation of node ID as input features. Also, I added target encoding, calculated using leave one out approach. The idea is pretty straightforward, so we're basically using labels of neighbors nodes to calculate average statistic of classes for a given node. Also, I calculate number of edges and Laplacian matrix. It's a common features in graph theory, in graph analysis. Some of my feature engineering didn't work, unfortunately, which was, for example, random walk target encoding. It's a combination of target encoding and random walk, which is taken from node to vec approach. Also, connected components as categorical feature, and also just numerical feature. For example, number of nodes in the connected component didn't work. I had a hypothesis that it's probable that we may have small subgraphs in our bigger graph, which are not connected to the big one, and we may add some new valuable information to our model by inducing this new feature, but unfortunately it wasn't the case. Also, I tested node to vec, and it did quite well, but unfortunately the training time of node to vec was too much to handle, and I decided to exclude it from the final solution. So in AutoML competition, you are aimed to show as high score as possible, but at the same time, you want to minimize your computational time, you want to fit as many models as possible, and you need to always make these decisions, like what approaches, what processings, and so on, include in the final solution, which shouldn't be included. After this data processing, I split my data into train and validation part. I used very simple approach, so it's basically a train while split. 15% of the data, 50% of the nodes came to the validation part, the rest come to the train part. And I used label of node for stratification. I used following models, which you can see on the slide. So basically, I used most of available models in PyTorch geometric. It is common approach in AutoML, let's put it this way. So you want to, the idea here is that you don't know beforehand which model will work for you the best. And you need to test as many models as you can. But of course, you specify the order which you are using for testing those models. So for example, here I used graph convolutional neural networks at first because they showed best score among nearly all dataset. Then I used LightGBM. And when I created my pipeline, I knew that in the end I'm going to stack my predictions together. And in order to improve the accuracy of stack, it is a good idea to include as diverse models as possible. So two points need to be addressed here. The first one, all models which are used for stacking should be accurate enough, and the variation of predictions should be also high. So by stacking or blending your models, you decrease this variation, and by doing so, you improve your final score. So that's why I decided to include LightGBM. It is a model which was trained on node features. And also I used several models which are just extensions of graph convolutional neural networks, such as graph convolution with attention, graph convolution with jumped knowledge, UNets, and others nets. So that's it for models. I also tested a lot of stuff, and of course most of them didn't work as expected. I want to share two approaches which actually did work quite well, but they were time inefficient. So the first one was label propagation algorithm. I call it label propagation on steroids. So the idea of label propagation algorithm is following. So you have a big graph, and some of nodes in this graph are unlabeled. And in order to train your model, you want to label those nodes. So you just propagate labels from neighbors' points, from neighbors' nodes several times, several iterations. And after several iterations, all nodes in your graph would be labeled, and you may use this as is, or you may use it for training your model. And this idea is pretty much similar to the pseudo labeling, in which we have a lot of unlabeled data and a small training data. So we train our model using small labeled data set, and then predict labels for unlabeled data. After doing that, we select a small portion from these pseudo-labeled examples and add them to our training data, and then train the model. So by doing so, you increase the size of the training data, and it is believed, and it was shown several times, that this approach may improve your final score on the holdout test data. So I decided to combine these two ideas, two approaches, into single one. So during model training, I actually made predictions for unseen nodes of graph, and on next iteration, on next epoch of training, I added this new label data into training data, and it actually worked, and it reduces the number of epochs which are needed for loss to coverage, and unfortunately, in some cases it helps a lot by reducing number of epochs, but in very few cases it actually dramatically reduced the score. And I decided not to include in the final this approach in the final solution. And the second approach is called diffusion. So the idea here is that when we are giving the graph, we may actually find new edges which are not presented in the graph itself, because, for example, there are no such edges, or we may have not perfectly labeled graph. So there is actually edge, but it's not in the data, and so on. So the idea here is that we want to reconstruct those absent labels, absent edges in the graph, and use this new graph for training our model. And this approach is actually smart, and I really like the paper. I really like how authors showed dramatic improve on several data sets. And I tested this approach in this competition, and it performed quite well, but it was really time consuming. So the problem here is that we need to find those unseen, unlabeled, absent edges. It takes some time, of course. And also, when we find those edges, we need to train our model, and model with more edges, with model which is trained on graph with nodes with more edges, would take much more time to train. To give you some understanding of the numbers, in my common solution, in my common submission, I had the time to train about 6 models, and when I applied this approach, when I applied diffusion, I barely could fit into training only half of the model. So basically, I was able only to fit half of the epochs which are needed for model training. And I decided to train more models instead of trying to optimize this approach. But again, if you are working with graphs on a day-to-day basis, I highly recommend you to check out this paper and check out this approach. And also some tricks which I used. So the first one, like the most important in automated machine learning, is the way how we should avoid a zero score. So in this competition, in very automated machine learning competition, if your submission fails, so for example, some exception is thrown, or maybe it was some memory error or stuff like that, or you just didn't return anything after time limit, you would get 0 score. And with this 0 score, your chances of winning would reduce dramatically. And we need to avoid that. So there are 3 ways which are used to avoid the 0 score submission, 0 score task. The first one is time tracking. So I track time for both training and inference. So I created early stuff in both for training and for inference. It's not the case, of course, for neural networks. There is no way you may stop making predictions in neural networks, but it is the case, for example, for light GBM. You may use reduced number of trees when you're making predictions. So I use this track time self-written class and also time pillow, so this small portion of time which is left just for case. Also, you need to prepare a most common class submission in the case of classification. So if your submission fails and you need to return at least something to avoid the 0 score. And like the most optimal solution in no model situation is just most common class submission in the case of accuracy. And also every line of my code is written under try except pattern. So the idea here is that it might be the case that your code works perfectly well for 99% of cases, but for 1%, only for one model out of 100, you would face a large graph, and maybe your model is large, and you would get like a good out of memory error, which happened to me, unfortunately, several times. And we want to avoid that. We want to avoid those rare cases, and the way to do that is to write as many try except lines as possible. Of course, it's not very robust. I don't recommend you to use it in production, but when you're solving a machine learning competition, I think it's fine. Also, like the second point here, if you left, if some time left, you don't need to waste it. You need to train as many models as possible. I'm sorry. So you may either optimize hyperparameters of your existing models, or as I did in this competition, I just train as many models as possible, and I trust my stacking approach. I believe that it can optimize the weight of each model in the end itself. Couple advices on model training. So like very basic LR finder, well, no rocket science here. Before training your model, try to find optimal learning rate, have some learning rate schedule here, and it will increase your score. And the second point, which I didn't find in any winner submission, is to use pre-trained weights. So in the case of machine learning graph, we don't have this ImageNet moment yet, but we may use something instead. So basically, in my submission, I did the following. So when I train, for example, graph convolutional neural network with 2 layers, and after that I want to train graph convolution with 4 layers, I don't initialize my 4 layers neural network with random weights, but instead I used first 2 layers from pre-trained neural network. And it actually helped quite a lot, because it reduces number of steps which are needed, number of epochs which are needed to train the model. For example, in some cases I reduced number of epochs from 150 to 100, which is quite a huge bump, and I recommend to try in your pipelines as well. And the final step, the final trick, is to use stacking. So in this competition, I used 3 models for stacking. Is their logistic regression with different penalty, with different regularization and different weight of penalty, and also random forest in LightGBM. So this was my overview of my solution. I came up on the 18th place, I think, out of about 50 participants, which I think is quite nice, because before that competition, I didn't work with graph data at all, and I think it's a nice result. And now let's discuss some solutions of top participants. So let's start from ODS AI participants. So the first one is Sergey Ivanov. He trained a simple GAT model. He did a simple hyperparameter search and used order stopping. So his model is quite simple, and the result was nice. Also, the second member of ODSIA is Svetoslav Kovalyov. The interesting thing about his solution is that he didn't use neural networks at all. So he created features himself, and it was quite surprising, because he achieved pretty nice place on the leaderboard without neural networks at all. And I think it's a good result. So I highly recommend you to check his code, which he open sourced. Now let's look at the top 10. So 6th place, the participant from 6th place, he created the pipeline with additional features, with reweighting samples, stuff like that. But the most interesting part here is automated EDA. The very idea here is that we create a meta model based on the features of the graph itself. So for example, here we may see that this participant used features such as directed or undirected, number edges, divided by number nodes, and many other features are just included only part of his meta model. And based on those features, he selected an optimal parameters of model, like model type and hyperparameters of the model. And I really like this idea. I don't think this particular implementation is scalable, but I like the idea in general. Second place is a team, PSA and GU. So they also used meta model as well, and their meta model is decision tree, in which they feed several features, and they want to predict configuration of models which are needed to be trained. So here we may see the decision tree itself, and for example here we may see that this leaf, the output, the predicted class is A, which means we need to use config A for training our model. And on the right, we may see an example of such config. We see there are several neural networks here, several architectures, and several hyperparameters of those architectures. I like the idea. Unfortunately, there are two major problems here, as I see it now. So the first one is that they used several features, and most important of them is number of features in node ID, which I think might be a slight overfit toward the data set that they were using for optimizing this stuff. I just don't see how number of features might be so important feature. And if we look at splits, we may also see that the borders are quite narrow here. And second problem is that when they're making predictions, they are making predictions of the list of the several models. So basically they are trying to fit single config file. I think it's better to replace this approach with just ranking your model. So basically I am proposing to use meta model in order to rank architecture of your neural network and parameters of your neural network, and then go one by one from most promising ones to the least promising one till you have time, and fit model one by one. Not a set of models, but models one by one. But the idea, the implementation, I really like how they did it. And the winner of this competition, so his solution is pretty easy, actually. He got two killing features here. So the first one is that he didn't use any additional features at all, but instead he actually removed some features from the node ID data based on the sparsity rate. So basically for each feature he calculated how many times this feature is not equal to 0, and if, for example, for 95% of nodes this feature is equal to 0, there is no too much sense to use this feature for training. We will just overfit our algorithm and we just drop this feature. This is actually quite a clever move. And second clever move is that he used node ID embedding layer in almost all models. I think all participants, and especially the participants in top 10, they actually used one-hot and code representation of the node ID, and embedding layer could actually improve the speed of learning. So you just replace this one-hot and code representation with a single layer. The speed of training will improve, the memory consumption will decrease, and so on and so forth. So basically, this is a smart move. and the common stuff like common models and learning rate finder. No big surprise here, I think. So basically that's it for my presentation. I hope you like it. If you have any questions, I would love to answer them. Thank you for your attention and bye-bye.